cleaning.
No, you can't imagine. I went in
Because
there several months ago and pulled out the computers to keep them up to date. And even then, it was looking dirty.
Yeah.
Hey, Mike.
Check 1, 2. Hello. Can you guys hear me yet?
Yes, I can hear you now.
I can hear you, David.
Finally, I got it going. I don't know what was going on.
You probably had it muted somehow.
I had to just make some changes here with my inputs. It's weird.
Anyway, Vance, yeah, we're gonna have to take a Monday as soon as they let us back in to take a Monday and clean up the place. Probably just
for sure.
Probably just take a hose and take a fire hose and just hose down the whole place because it's gonna be a mess.
I don't know what it's going to take, but it's going to be a lot of work. It was looking pretty bad when I was in there getting the computers.
Yeah, we can't do that on a Wednesday, so we got to do that. We got to do that on a Monday.
For sure.
Yep, all of us. And the people in the workshop, I've got to clean up their area. You and I will do the observatory.
We'll do the dome and everything on the stairway and get everything up and running again.
Yeah.
It'll be a big job, but it's worth doing because I'm really looking forward to doing this again.
Yeah. Oh, and at Griffith, they assure me that they kept the place clean, but I happen to know nobody's been in that planetarium, to my knowledge, for a long time, and I know critters live in there. I have to monthly go in there and clean it because I'm the only one authorized to do so. Well, there you go.
Lucky you.
Now, is Curtis or Tim or one of our presidentes with us?
Tim will not make it tonight, apparently.
Who?
Tim.
Oh, no.
He said he wouldn't be able to make it tonight.
Yeah. Phil, can you hear me okay?
Yep.
Good.
Yeah, I can now.
What's
Annie,
his
you're
excuse?
muted.
The electrons are doing the moving for him.
Yes, I know I was muted, not anymore.
Okay. Nice to see
There's
you.
Annie. All right.
Hi.
Hi. Joe, how are you? Missed you at the board meeting.
Yeah, I'm doing pretty good.
Good. You look good.
This is to be your first official meeting, right?
Yes, apparently. Yep. I thought
This
it
is
was
the
Wednesday.
First general.
Yep.
Yeah, that's true. This I haven't seen Ralph check in yet, but he probably will. Get our new board member.
I think I just saw Curtis come in.
Yeah, I'm on here.
Okay, Curtis. There he is.
Here he is.
We better clean up the act.
Yeah, you guys better clear up the act.
Everybody go
Wait
hide.
a minute. I thought you said Tim wasn't going to join us. Why do we have to clean up?
No, he's not. He said he
Why have to
wasn't.
clean up for this character?
Because you're being live streamed to YouTube.
Good to see you, David Nakamoto.
Okay, thanks.
How many do we have so far, Spencer?
We've got 31 people.
Wow.
31. I will, in fact, we will go ahead and get the meeting started. It's officially 8:03. This is the January 2021 meeting of LA Astronomical Society, the general meeting. Normally we would have a banquet at this sometime during this month for this meeting, but since we have the COVID, we will not be having a banquet this year. And unfortunately, that's the time when we all go out and have a good night out on the evening. Well, anyway, we're kind of stuck with doing this with the Zoom meetings. First thing I would like to do for tonight, do we have any announcements as far as any announcements that I know of? I will leave the announcements to the committee reports, announcements as far as Lockwood Valley and Ford Observatory. I don't know. Do you know of any other announcements we need to make, Spencer?
Just a couple of notes. Meeting's been recording to YouTube, and secondly, I've just posted the link for the door prize drawings on the chat. So go ahead and fill that form out, and we'll have the drawing at the end of the meeting.
Okay, it looks like we're probably ready to go. What I would like to do, since this is the January meeting, and this is the meeting that we introduce the officers and the board of directors for year 2021, which the official board will meet for the first time in February at the board meeting. So I would like to introduce the the officers and the board of directors. Everybody should know me. I'm Curtis Byram, the president of LA Astronomical Society. And the next one is Vice President Alicia Hurst. Is she online?
Don't see her here.
I've not seen her.
Oh, she's not here yet, huh?
Nope, maybe not.
Hopefully she makes it in. Spencer Soho, I think everybody knows Spencer. He's the guy with the Northern Lights behind him.
Yep.
Spencer, if you'd like to make a statement, go ahead.
Hello, everybody. Wish I were there.
I think everybody knows Spencer. Our treasurer is
Spencer. Wish
yes?
you were where?
Huh?
Spencer, wish you were where?
Iceland. That was Northern Iceland.
Ah, got it. Okay. Sorry.
And our treasurer is John O'Brien, the one that's got the fuzzy hair and fuzzy beard. Yeah. Would you like to say something, John?
I'll be glad when the barber shop opens back up.
Well, your wife can always put a bowl on your head and cut around it.
I don't let her near my throat with sharp objects.
Oh, no.
Oh, that's harsh.
Ooh, that was a real cut. Excuse me.
And the puns continue.
So the returning board of directors, Daryl Dooley, would you like to make a statement?
Glad to be here for another year. Hope we can do something this year.
Yeah.
That's true. Hopefully we can. Kevin,
let me say one more thing.
Yeah.
What we are doing something, and one of the things that we're doing is what we're doing right now. And it's turning out that these Zoom meetings for the board meeting, and especially for the general meeting, are turning out to be a very good thing. And I think that when we continue, even when we are back in the Leonard Nimoy Theater, that we should absolutely do this as well. Because there's a lot of people that are here, like Mr. iPad, he's in Colorado. So it's really nice. I see more people at the Zoom meetings than I ever saw at the general meetings regularly. So I think it's a good thing. Let's keep doing it.
I think it's a good idea too, because I can't get out to the meetings very well, but this I can do.
Yeah. Right. And a lot of people, when they find out that they can do this and that it works pretty well, and that, we've had speakers, and the speaker's presentation is not too much different than when we're at the Leonard Nimoy Theater. So it's real close and it's really good. So everyone keep coming. Tell your friends.
Thank you.
Okay, thank you, Daryl.
And join, because and if you join the club, if you're not a member, you get to have all these cool things too.
Yeah, we have this fun. This club, we do have a lot of fun in this club, no doubt about it. And hopefully we can get Matt Wilson and all the activities going again very soon here.
Yeah, no kidding.
Yeah, Kevin Gilchrist, he's the currently the committee chairman for Lockwood Valley. Kevin, you out there?
Yes, I'm here. Hello, everybody.
Hey, Kevin.
Hey, Kevin.
Hi. And well, of course, everything is closed down for COVID's sake right now. So hopefully the world gets its act together and we can all get our vaccinations and we can go back out and enjoy each other's company. And I'd also just like to add, it wasn't me. I was not in the Capitol last Wednesday. I see so many faces that kind of like look like mine, blah.
Facial recognition is getting better.
Blah looking white men,
We got facial recognition, Kevin. Don't you worry.
Yeah.
We'll find you.
Okay. Well, hope to see everybody sometime in Lockwood.
Yeah. Well, maybe not Lockwood.
Okay, thank you, Kevin.
It.
The next board member, Mike Hayford, is he out there tonight?
Yep. Yeah, I'm here.
Okay, would like to make a statement?
Glad to be back on the board. Again, just kind of reiterating the themes others have had is looking it's nice to have Zoom as an option, but being able to be there in person and to go to Lockwood and Mount Wilson and Garvey and Griffith, I'm looking forward to that being possible again in the not too distant future.
Okay, thank you, Mike. Joe Phipps, you're out there. I know I heard you.
I'm here. Thanks for electing me again. Yeah, it's unfortunate everything is closed down right now. We can't see each other like we normally did, but maybe at Ford Observatory we'll be able to have some small events after ski season and the lights get turned off, and hopefully everything else opens back up this year. All we can do is hope.
Yeah, currently Ford Observatory is closed down. Joe and I are probably going to try to get in there in the next couple of weeks to see if there's any water on the floor, because I think we got over a foot of snow over there at Ford. So we got to see if the dome is relatively sealed and see if we got any roof leaks. So that's probably what we're going to do in the next couple of weeks if we can get in there. I don't think we'll have too much of a problem getting in there. But anyway, the next board member is Greg Thompson. Greg, you there?
Hi.
Would you like to make a statement?
Oh, sure. We're not miss a chance to run my mouth.
Never.
I got the haircut that John was talking about. So
looks good.
A front porch special. The whole neighborhood got to see the buzzer come out, and at least my
public humiliation.
Well, at least the hair isn't hanging down in my eyes anymore, so that's good.
Scout merit badge for that.
Yeah. From the scout meeting where I was teaching a merit badge, here I am in my thing.
Oh,
all right.
I will mention that our program, even though it was fully virtualized over this last summer, was very successful. Hundreds of scouts earned the badge. Many members contributed, and I would thank those that did. And we are, in the next month or two, we're going to be setting up our program for this summer, which is going to have, you know, if we're open and it's safe, maybe we can do some live things again. Hooray. There's nothing like having the scouts look through actual telescopes. Garvey is a great site to teach that badge, but we can do it virtual again. And we'll be planning that. And I just thank the opportunity to serve on the board. It's a great group and a great club. And, you know, I love going up to Griffith Park on public star party night and seeing all my friends, as well as show the public what we do. So looking forward to that when it's, and it could be a while, but I'm looking forward to it.
Greg, is it acceptable to jump in here and ask a quick question?
Sure.
You talk about outreach virtually. I have been seeing those things mentioned and I don't get it. How are you doing that? What are you actually doing?
So we designed a program in March and April of this year to take our astronomy merit badge class online with the support of the board and the club, both as individual volunteers, and they provided the Zoom account and the planning, and then I had a series of demos based on a webcam in my house and some PowerPoint slides for the requirements of the merit badge, which I use when I teach it live as well. Probably the most exciting part for the scouts was, I think at all 3 or 4 classes we did over the summer, Spencer joined from his laptop while it was connected to his telescope in his at his house up in the mountains, and the scouts were able to live view by having him share the display screen from the software and ask questions about what they were seeing, and he could slew it around, and we had some planet viewing. I won't say conditions were the best and we saw the greatest views, but the scouts don't know that. They thought it was absolutely amazing to see Jupiter or Saturn or the Ring Nebula or something like that. I also had some slides, some astrophotography slides that I used with permission, which I would like to do again because I know we have some great astrophotographers. So it's, you know, only 80% of the live experience, but we did everything we can to keep the audio visual interaction live to make it more interesting for outreach. And I think the merit badge class is kind of a primer on something that we could do that Curtis has me looking into for this summer, which is to do our own seminar with live demos and live viewing through the digital technology, and maybe do an astrophotography class. So, if you're interested in seeing that go forward, email Curtis and we'll get it organized. I think we have some great knowledge and skills, and I could call on maybe a panel of 3 or 4 to do demos or presentations, and then everyone could participate just like they do in the general. So I think we can do, it's not as good as being live in person. I agree with that, but it's better than sitting around doing nothing. And I think with the experience we have in the club, it would be well worth to do an online seminar.
I completely agree, actually. And interesting, the way you described it is because that is the way I do my astrophotography. I'm not an astronomer at any level. I'm an artist. I aim a scope at the sky and find ways to capture pretty stuff. But at the same time, it's all through a remote system, even though it's in my front yard. So I could actually share my laptop screen as you described, and wondered if that's what you were talking about.
Yep. So when I get around, I may post on the boards if you follow theirs, or send out a general communication. If we have some virtual badge classes going for this summer, I absolutely would look for volunteers to do exactly that kind of stuff and make it more interesting for the Scouts. It's the best we can do to share what we do with young people, and sparking that interest is, that they're the future. And it's one of the ways, it's 100 times more than they get up at Griffith Park, right? They have to actually learn quite a bit about telescopes and the night sky and that sort of stuff. So it's not super intensive. It's only like 2-3 hours, but to earn the badge, they actually have to do a fair amount, and it's a good opportunity. And thank you for, I'll get that. When we're organizing it, I'll get a post or some email out and ask if anyone would be willing to volunteer for those this summer. Thank you.
Thank you.
Thank you, Greg. Do appreciate that. Another board member, Tim Thompson. He is not with us tonight. He had a leg injury, so we don't know how serious that leg injury is. So I will go to the 2 new board members. Ralph Gonzalez, are you out there?
Muted. Got your mic off, Ralph.
Is he out there?
I don't see his name on the list.
Yeah, there's a Raphael G. That's probably.
That's not him. Maybe he didn't make it.
It's possible. Okay, the next one is David Yackerson. Is he out there?
I'm here. Can you hear me okay?
I heard him earlier.
Yes, Dave.
First, thank you guys. I'm honored and looking forward to being helpful to all the membership of the of our group, and I'm anxious to listen to every new members, all the original members and existing members, and to anything I can do to be helpful for the group. And also, I'm really thankful for letting me have this opportunity. So thanks a lot. I sure appreciate it.
Hey, thank you, Dave. Nice to have you on board.
Thank you.
Okay. So the LAS membership, that was a presentation, at least what you can see of our new board for 2021. Okay, the next order of business at the general meeting here is the committee reports. I think Kevin has already mentioned that Lockwood Valley is closed because of the COVID. Ford Observatory is now closed because of this. The local ski area is skiing at night, so we kind of lose Ford. Is there any other comments that Kevin or John would like to make on the Lockwood Valley?
This is Kevin. No, I think I've covered it. I leave it up to John if he has something to add.
I would like to remind everybody that we are closed due to COVID, and we are asking STAR members, even though we're not having activities up there, STAR members are still allowed to access the property. But we are asking all the STAR members to go online and fill out the notice or registration, whatever you want to call it, to let us know that someone is out there and that they are aware of the restrictions and will abide by the restrictions. Just one other thing, the new restroom, the toilet is still broken. So if you do go up there, you have to use the old restroom. And apparently the new toilet, somebody left water in the bowl and it froze. And so we'll be posting a more detailed instructions on how to operate the toilet in the wintertime, so we don't have that problem in the future.
Hey, John?
Not anything else particular going on up there because of the weather and COVID, of course. Yes.
John, I'm sorry to interrupt. We have a Lockwood committee meeting next week, correct?
I believe it's the 20th.
Yeah, it's
the
January
20th.
20th.
Yes. So it'll be online 8 o'clock, just
It's
like this.
COVID. Why? Who knows what day it is? Oh, so 10 days. Okay. You mentioned the toilet froze up. Would maybe adding a bottle of antifreeze to our dump bucket solution?
There is antifreeze up there for the sink. The toilet is gravity flush. It's not supposed to have water in the bowl. You're not supposed to.
Oh, right. So it was a mistake that happened. Got it. Okay. The other question about Lockwood, and this might not be appropriate for this meeting, I'm not sure. Because COVID is obviously going to continue and parties are gone and all that, how do we go about going for a star membership at this point? In other words, I would like to be able to go up once a month or so on the odd night, having nothing to do with, family nights and all that stuff. So obviously I would need to go for a membership. How does that work? What do we do now?
Members who've been a member for at least a year fill out an application for star membership, and the application has to be signed by 2 sponsors who are other star members who will be your sponsor for star membership.
Got it. Okay. All right.
Curtis,
so I'll look that up online and go from there and see if 2 of you guys are willing to sign for me.
Curtis, you forgot to welcome the new members.
Yeah, we do have a lot of them. In fact, the board, last time we had our board meeting, everybody was given numbers to call new members. How many of the board members were actually able to get a hold of the members that they were asked to call? The person I was asked to call, I left a message. I called them 3 or 4 times, left a message. They didn't return the call. So how did that work out for the rest of the board?
I got 2 out of 3.
I had success, and I think Mike is here tonight.
Oh, okay, good.
I left a message, but I haven't heard back from them.
And I see one of the people I talked to, Stanford Hill.
Well, that's good. That's good. Yeah, I'm just trying.
Yeah, welcome to the new members. That's great.
Yes, welcome to the new members. Normally, I mean, we do this in the meeting, but I can't see who's online or whatever. Who's like Spencer said, what are 35 members now or 40 on the?
We've got 38 on.
38 online now, so I can only see 4 on the bottom of my iPad screen here.
Do any of the new members want to introduce themselves if they have video or not?
Yeah, I will. I'm Mike Martin.
Hi,
Sorry.
Mike.
Hi, guys.
Hi,
I
Michael.
just joined. We joined with a family membership. My daughter's she's very into astronomy, and she wants to learn a bunch of stuff, as do I. And we're very interested in doing some astrophotography. So, if anybody can help us out on that, that would be awesome. So,
Boy, you're in the right place.
yeah. I thought so.
Welcome.
Thank you.
Mike.
Welcome to the club.
Thanks.
Hopefully we'll be able to get back and start doing some neat, fun things. That's why everybody likes to join this club. We do a lot of neat things at this club.
Anybody else?
Any other new members?
Yeah, my name is Stan Hill, Stanford Hill, but I go by Stan. And my wife and I are members. I was a member, I think, in 82 and 83. In fact, I was on the board one of those years. So I'm finally back after,
40 years.
40 years or so.
Is that all?
Welcome.
Perfect timing. Perfect timing.
Yeah.
Welcome back.
Next new members?
Can
Any other
anybody
new
hear me?
members? Yes.
Can you guys hear?
Yes.
Can you guys hear me?
Yes.
I'm Rafael Gonzalez, and I just want to say thank you for allowing me to join the club. I'm very excited to share ideas and share my opinion in this club, and hopefully I can help people with astrophotography. That's kind of what I do. And
Kind of looking like
I'm
it
very
by your
excited.
background there.
Thank you guys.
Mm-hmm.
Yeah, I can't see myself, but I was having some technical issues here earlier. I couldn't figure it out how to get my computer was glitching. But I got it figured out now. So
Welcome.
welcome
Welcome.
you guys.
Welcome to the board, Ralph.
Thank you.
Do you guys have time for a very brief, interesting story?
We got a lot to do tonight.
That's why.
Yeah, I think we better go on to the finish up with the new members and then go on to our speaker.
Stories at the end.
Yes,
got
we can do it at the end.
Remind me, you'll like it. I put my hat on, the LAAS hat.
Just a reminder for anybody who missed it. There's if you look at the chat, and I'll repost it. That's the link for the door prizes.
Oh, that's where I got my hat. I won the door prize last month.
It works.
Yes.
Yes, it's working.
What's going on, Joe?
Okay.
Go ahead, Curtis.
Any other new
Okay,
members?
so we'll go on to our guest speaker for this evening. His name is Jeff Rich. I will let Spencer take over and introduce our guest speaker for tonight since he knows more information. Spencer, it's yours.
Okay. Well, I was actually going to have Tom introduce Jeff since Tom knows Jeff. So the best I can do is basically read his bio that he sent me. So he's an astronomer at the Carnegie Observatories. He runs the outreach and education programs at the observatories, and he studies galaxy mergers and how fast the universe is expanding. He's from Washington State and pursued undergrad studies at USC and graduate work at University of Hawaii. So Jeff, you want to take it from there?
Sure. Thank you very much. I appreciate y'all having me here virtually. I hope someday I can actually come to an in-person meeting. I think it could be really fun. So I'm here to talk about galaxy mergers, and I'm gonna share my screen, right? You all?
Sure, yeah.
Is that all right?
I'm going to stop sharing. Okay, you've got it.
Okay. The almost year-long tradition of doing. All right, everybody can see a beautiful galaxy merger. Wonderful. So
we can see the whole thing, including the slides on the side as well.
interesting. I think that's a. Let's see if I can do
Slide mode.
slide mode.
I don't know where you find it.
Or you might
Slide
double-
only. It's you were right there.
Sorry about that.
Yeah, under navigator.
Yeah.
Navigator. Oh, slide only. Gotcha. Thank you.
You're welcome.
There we go.
Better. Thank you.
That's much better.
Y'all are veterans. Thanks. So,
And that's pretty.
That's a beautiful image, by the way.
That's pretty.
So this is one of my favorite galaxy mergers. It's going to come back to haunt us throughout this talk. This is NGC 3256. It's one of the more nearby luminous infrared galaxies. But by the way, since I work at the Carnegie Observatories and I am the outreach person, I always do an obligatory reminder about Carnegie, though many of you probably already know we've been in Pasadena since 1904. And right now, all of our modern telescopes are located down in Chile. And just as an update, if you didn't already know, we're now observing remotely with the Magellan telescopes. So there are folks here in Pasadena and elsewhere using Bada and Clay to continue observing, even though we can't go down to the observatory anymore, which is a bummer, but at least we can keep doing science. And if you haven't already visited, I hope you will someday. We have an open house every October. We have a lot of great scientists and engineers and staff who are doing really cool stuff. And normally I would be advertising our annual open house. I would be saying how great it was and how you should all come to next year's. Obviously, this last year we didn't have our open house. We had a virtual open house. So if you haven't already checked it out, we did some video content for the first time, and you can visit our website and take a look. We decided to make some videos of places that we can't usually open during the open house, including our plate vault and the grading ruling engines in our sub basement. It's something that I really like to share with folks, but for logistical reasons, it's something that we can't open to the public when we have a few hundred people on our campus. And we also had a bunch of Ask an Astronomer questions, so you can take a look at those and meet some of our other folks. And we did a virtual star party for the conjunction with Mount Wilson and with Glendale Community College. Some of you might have watched it. If you haven't, the video is online. We did live views through an 8-inch Schmidt Cassegrain run by Chris Burns and Jenny Cresto. And we also had a couple of views through the 60-inch of Mars and a planetary nebula, but really the star of the show was Jupiter and Saturn. I thought folks would be really excited to see live views through the 60-inch, but you can't compete with how amazing it was to see those two planets close together. Anyway, science. Okay. I like to start my talks with a little bit of background. So just a reminder, I'm going to be talking about galaxies and galaxy mergers. I'm sure you all know what a galaxy is, but scientifically, just so we're all on the same page, it's everything bound together by gravity that's stars, stellar remnants, interstellar gas, dust, and dark matter. The fun thing about galaxies is they come in a huge range of sizes and shapes and colors and morphologies. So this is one of the more fun comparison charts that I found online. The picture in the middle is a simulated image of the Milky Way with a few other galaxies around it, roughly to scale. Some of them are familiar, like M82 and the Sombrero. But just as a reminder, galaxies can be as
Jeff,
small as...
Are you sharing your other screen? Or just seeing your first page,
Have my slides not been going?
Yeah, nope.
Oh, boy.
Ah, there we go.
Ah, much better.
Interesting. So, so when I do this, what do y'all see?
Now we have that slide.
So let me know if I tab over. Do you see? Are things changing at all?
See a slide with galaxies, many shapes and sizes, range in size, blah blah blah, and about 15 image up. Now we have titles and bullets on the right hand side with your formatting, and basically we're seeing the program.
Gotcha. Okay.
And now you're moving your mouse from slide only to oh no, you left it.
So you can see everything. All right. Well, that's okay.
This is acceptable.
You know what? We're gonna do it this way. So
nothing wrong with that. It'll work.
Thanks very much. You missed a couple pictures of the Carnegie observatories, but that's okay. So now you can at least see the galaxies. This image has the Milky Way in the middle and a few galaxies around it. It's just to show how galaxies are really in all shapes and sizes. And for those of you sneaking a peek at the next slide, I like this one because it puts the Milky Way in the middle again, but not quite as large. And it's cheating a bit because the really, really large structure on the left is giant radio lobes. But just to say, galaxies are really all shapes and sizes. But as an astronomer, what we want to do is really understand all of the possible things about them that we can. I'm an observer, so I like to share this slide for folks who want to know how it is we actually study galaxies. As an observer, I like to look at galaxies and try to figure out what it is I'm looking at. But there are people that work at the Carnegie observatories who spend their time making computer simulations of galaxies, of single galaxies, of ensembles, of the entire universe, to try to recreate what we see. And in reality, we talk back and forth and try to make sense of whether our observations are matching the simulations and vice versa. The old joke is that if the simulation doesn't match the data, if you're a theorist, it means the data is wrong. And if you're an observer, it means the simulation is wrong. And one of the first things that we talk about with kids when we're talking about galaxies, one of my favorite activities to do is to give a bunch of flashcards of just pictures of galaxies with no other information, and ask them to sort the pictures by anything. We say, however you want to do it, put them into groups. And most kids will actually recreate the Hubble type classification more or less. Just looking at pictures of galaxies, it's really obvious that some of them are fuzzy and diffuse and elliptical, and some of them are spirals. And then there are those that don't really fit into the picture, and you can chuck them over into the irregular bin. And the Hubble type classification was an early attempt at just sort of trying to make sense of what are all the galaxies that we're seeing and what are the differences. Now, the next step is trying to explain how those differences come about, right? We have that old habit of holding on to the old nomenclature of early type versus late type, even though it's not what we think happens to galaxies. So in this old picture, galaxies on the left are early type and galaxies on the right are late type. When it's not really clear that that's what happens, they might go back and forth, probably right to left. And aside from just looking at visual differences in shape, astronomers have really classed things into color and size. And there are these really broad properties that we see as a result of that. So we see that galaxies seem to be split into blue and red, which is things that are making stars and things that are no longer making stars. There are a handful of galaxies that are in between, but most galaxies fall into one of these two bins, right? And it looks like the most massive galaxies are red and dead. And then you have a bunch of other galaxies that range from low to high mass in the blue star forming cloud. And that's due to the fact that when you're making stars, those young, hot, massive stars are bright and blue. They don't live very long. So if you give a galaxy 100 million years and it stops making stars, it'll very quickly turn from blue to red. So this is the picture of astronomers trying to understand galaxy evolution. A lot of studies, whether it's looking at thousands of galaxies and trying to piece their different properties together, or looking at a few single galaxies and trying to understand how a galaxy grows and how it changes from a small to a big galaxy, or whether it goes from star forming to non-star forming. This sort of arrows and question marks are the broad strokes of what astronomers are trying to understand when they look at galaxy evolution. And this encompasses a whole bunch of different studies, but any single galaxy in its lifetime will probably go through a bunch of different phases. It'll obviously start out relatively small. It will grow bigger as it forms lots of stars. It may run out of, it may stop forming stars and become red. It may then find a new source of fuel and start forming stars again. So any single galaxy will get bigger and go through a number of different processes. And a lot of astronomers are just trying to understand the entire picture and how you go from blue to red and small to big. So the big questions are, how do galaxies grow and change? What are the mechanisms that start and stop star formation? And how can we catch galaxies in the act going from star forming to non-star forming or small to big? There are lots of different ways to approach that question. And this is, again, something that factors into folks trying to compare observation and simulation. So there are plenty of astrophysicists who build sort of universes in a box, or even a single galaxy in a box, to try to recreate this process. And the number one thing that a lot of us are looking at as observational astronomers is gas. It's the source of fuel for star formation. You need gas to make new stars. More importantly, the gas has to be able to cool to make new stars. You can't make stars unless the gas is able to cool and collapse into dense clouds, and then ultimately make new protostars. So if you either use up all your gas, remove the gas, so throw it out of the galaxy somehow, or you create an environment that doesn't allow the gas to cool and become dense and collapse, star formation will cease to happen. So there are different ways for that to happen, but this is the sort of fundamental thing that you look for when you're thinking about whether a galaxy is going to make new stars, or whether it's sort of done making stars, or whether it might change its mind at some point. You can keep making your galaxy bigger and forming new stars as long as you have a source of gas and you can keep it cool. But if you get rid of that gas, or you are in an environment where the gas is too hot, you're going to quickly move up to that red sequence of galaxies and stay red and dead. And you might get bigger by merging. One place we see this is galaxy clusters, where you have galaxies that can be done forming stars, but might merge with other galaxies that are done forming stars. And they can get bigger that way and stay red. So one of the things that I'm really interested in is looking at outflows and inflows, tracking the gas. If you have one of these galaxies like M82, the Cigar Galaxy, it's got a pretty active starburst going on. So if you look at it in this image on the right, taken by Hubble Space Telescope, the red is hydrogen alpha, so gas that's being lit up. You'll notice it's being blown out of the galaxy. So when you have an intense burst of star formation, you can have massive outflows that drive gas out of the galaxy in a big galactic wind. You can also have a situation where an active galactic nucleus, the supermassive black hole at the center of a galaxy, forms a large accretion disk, gives off lots of energy, and that can also drive a galactic wind. So this is a process that can throw gas out of a galaxy and ultimately help speed up the end of star formation. So finally, luminous infrared galaxies. The reason I'm here to talk to you about luminous infrared galaxies is because they are sites of intense star formation, and they tend to host active galactic nuclei. So they're where the universe is making lots of stars and undergoing lots of change. The definition of an ultraluminous or luminous infrared galaxy is a galaxy who gives off most of its light in the infrared. And we're talking huge amounts of light. The cutoff for a luminous infrared galaxy is 10 to the 11 solar luminosities. For an ultraluminous, it's 10 to the 12 solar luminosities. So, you know, 1 trillion suns worth of light just in the infrared. The picture on the right is obviously a beautiful Hubble Space Telescope image in blue and infrared light, near infrared light. But most of the light in these luminous infrared galaxies is coming from these really intense processes like starbursts or an active galactic nucleus that's giving off actually short wavelength light, ultraviolet, very intense hard radiation that gets absorbed by dust in these galaxies, which then heats up and re-emits the light at longer wavelengths. These galaxies were first discovered by the IRAS satellite in the 1980s, which went up and looked at the sky in the mid and far infrared for the first time and saw a lot of really, really bright sources that turned out to be associated with galaxies. The image on the right is an example of a relatively nearby luminous infrared galaxy. And you'll notice it looks like a bit of a train wreck. It's in the southern hemisphere. It's VV114. It's one of my other favorite nearby luminous infrared galaxies. And it's not a coincidence. If you go look at the nearby luminous infrared galaxies, so once IRAS discovered these things in the 80s, astronomers went and double checked images that were already available and followed up. A lot of the luminous infrared galaxies in the local universe look like train wrecks. That it looks, many of them look like they're currently in the process of merging. They're about to merge. They may have already merged. So two really massive galaxies coming together. And these luminous infrared galaxies are forming stars at an incredibly intense rate. So even the less luminous infrared galaxies are making stars at a rate of like 10 solar masses a year. The brightest ones can have intense bursts of 100 or hundreds of solar masses a year. So they're making stars incredibly rapidly. That means they're building up stellar mass quickly. If you were able to maintain a rate of 10 to 100 solar masses a year for 1 million years, which is a blink of an eye in cosmological time, you've grown yourself by 100 million solar masses. That's pretty significant. So these galaxies are really interesting. We look at them because they're doing something intense and changing quickly. And I like to show this. It's black and white images, but that VV114, that beautiful sort of train wreck merger, this is an image of the same galaxy at different wavelengths, all the way out to the radio, just to show how if you look beyond the visible, the light is really usually dominated by a compact infrared source, something that's much more spatially dense and associated with either an intense starburst or one of these active galactic nuclei, sort of actively accreting mass. And for VV114, well, it's a bit of both, but I'll come back to that later. Oops, sorry. So I also like to show this image because it's a nice color image that shows the difference. It's kind of fun because for this galaxy, to Zwicky 96, on the left, you see just the HST visible light and near infrared image. It's a beautiful galaxy merger. There's a lot happening. There are stars forming. There's probably shock fronts and really cool things going on. But when you add in the mid-infrared light from the Spitzer Space Telescope, you see this intense glow that's completely buried by dust that you just don't see at visible or even near infrared wavelengths. So with these galaxies, it really pays to go and look at them at many different wavelengths because you can see light that you wouldn't otherwise see at visible wavelengths. Now I say that, and I hope you remember because I'm going to talk a lot about looking at them at visible wavelengths and why that's really interesting. But just to note, these things are really unique, interesting looking objects that aren't your everyday galaxies. And the bigger picture that grew out of looking at these major galaxy mergers that in the local universe were often luminous infrared galaxies is that undergoing the merging process, so sort of throwing two gas-rich star-forming spiral galaxies at each other, the whole process takes only about maybe 1 billion years, which isn't that long in the lifetime of a galaxy, but that the process is very transformative. It causes a huge burst in star formation. It helps not only make a bunch of stars, but blow a lot of the gas that's the fuel for star formation sort of out of the galaxy into the halo of each of the galaxies. And it turns these two blue star-forming galaxies into a red elliptical. So it's one way that astronomers think you can go from the blue cloud of star-forming galaxies up to the red sequence. And you're taking something that was two smaller galaxies and turning them into something that is even more big than the sum of their parts. And this is something that astronomers have been modeling for a very long time. So the sort of canonical scenario in computer models is throwing two galaxies at each other. When that happens, the tidal forces on the gas actually cause the available gas in the galaxies to flow towards the nucleus of each galaxy. So it tends to concentrate the star formation at the centers of the two galaxies as they're merging. You see tails of gas that can form stars as well, but you see really a lot of intense activity in the nuclei, which is predicted by models and then is borne out in observations of the galaxies that we look at as well. That you see the gas being whipped around and the stars themselves being pulled and tugged by tidal forces. But when you look in the mid-infrared, as I mentioned, for a galaxy like Zwicky 96, you see really compact bursts of star formation or active galactic nuclei. And just as a reminder, many of you probably already know, this is probably going to happen to the Milky Way. We're headed straight towards Andromeda, or Andromeda is headed straight towards us. And we're both relatively large spiral galaxies that are still making stars with a decent amount of gas. In a few gigayears, we will probably look like one of these train wreck beautiful luminous infrared galaxies. The Milky Way and Andromeda will probably undergo a really massive starburst, go through this process, and leave the universe with a new galaxy that is probably a massive elliptical, which, unless something has changed, the only name I've seen is Milkomeda. So you have a 5 gigayears to come up with a better name. So all that said, how do we look at these galaxies? We think they're an interesting set of galaxies to study because we have a few of them relatively nearby, and we think they're undergoing a transformative process that it would be useful to drill down deep and look closely at whatever's happening inside of them. I mentioned that there's observers and theorists. I'm an observer, so I ask how to observe them. How would you actually look at them? Well, the first thing that comes to mind is what I already mentioned. Look at them, take images of them at wavelengths from the X-ray to the radio, sort of use every possible telescope you can to look at the stars, look at the gas, look at what the supermassive black holes in the centers of these galaxies are doing, to measure how the merger process changes the galaxies before, during, and after. We don't have the benefit of waiting a billion years to watch the merger happen, but we at least have a large enough sample of merging luminous infrared galaxies that we can kind of catch them at different stages and try to piece together what happens during the process. Now, imaging is great and beautiful, but I'm a spectroscopist. I actually like to take these galaxies and take the light and split it and learn even more. So I wanted to stop and take a minute and give a really quick primer on spectroscopy, because imaging is beautiful. It's the number one way we love to show off how amazing the universe is. But spectroscopy is sort of the nuts and bolts of how we understand the physical processes that are happening in these galaxies.
Can I jump in for a moment?
Please.
I don't for an instant understand that word. Can you explain it?
Absolutely. Spectroscopy?
Yeah, some of us are astrophotographers, not astronomers. So I'm trying to keep up with you.
I'm glad you asked, and I'm really glad that here's where I want to actually start from the beginning. So to answer that question, I usually start with Isaac Newton. And the short answer is it's literally taking the light from an object and splitting it into a rainbow. And that rainbow tells you something about the light that you're looking at. And people had seen rainbows and had seen how you could split light even before Isaac Newton. But what Isaac Newton proposed was that when you take the light from an object like the sun and you split it, the rainbow that you see is telling you something about the source of light. So if you look at a rainbow of the sun that you've generated with a prism, that rainbow is telling you about the source, not some, it's not the prism itself. And that rainbow is a spectrum. And spectrum is a generic English word that can mean a lot of different things, but from the scientific standpoint, when we say spectra, spectrum, spectroscopy, it's taking light and splitting it into that rainbow. Most of the time in my talk, I'm going to be talking about visible light spectroscopy, but that term is broadly applicable. So there are radio astronomers who look at radio waves and split them into different wavelengths or energies. Ultraviolet light, you can do the same thing. Infrared light, you can do the same thing. But the basic concept is splitting light and looking at the intensity of light at each color, at each wavelength.
So that actually corresponds to the fact that since I'm taking pictures with a monochrome camera and filters, each one of my filters, for instance, hydrogen alpha, sulfur, oxygen, that's using the word, the spectrometry aspect of what we're attempting to see out there.
Exactly. Imaging, as it's usually it's done in the monochrome, you would use say a blue filter, even a blue filter or a red filter. So these images I've been showing of luminous infrared galaxies, the galaxy on the right is a composite of a blue B and I, so blue and not quite red light. That is actually really at a really basic level telling you something about the physics, the color of what's happening in that galaxy. If there's more blue light versus red light, that's telling you something. You can take that a step further and analyze the light in more detail. So take that light and really measure at each color how much light you're getting in an even more fine-tuned manner. A really good example of that would be the sun spectrum. So, going from Isaac Newton to Fraunhofer in the 19th century, people expanded on this idea and noticed that if you take the sun's light and split it and look very closely at the resulting spectrum, there are all these dark bands. And those dark bands, folks figured out relatively quickly, corresponded to different elements in the sun's spectrum. So that if you're able to look very closely and carefully at a spectrum, it can tell you a lot more than you would get otherwise just by looking at the light. As you said, now we are even better off because we just have narrowband filters that can narrow out everything except a very narrow piece of the spectrum, as that wasn't something you could really do in the 19th century. Just really quickly, when we take the light from an object and split it, there are three sort of basic kinds of spectra that are common. One is a continuous spectrum, which is anything that has a temperature is giving off black body radiation. I won't get into the details. Basically, a light bulb, an incandescent light bulb gives you a continuous spectrum, and the temperature will shift how much light you're getting, red, orange, blue. We don't usually see those in space. What we see in space is either an emission spectrum, which is a hot gas made out of different elements that's being excited by some source of energy. And you see these very discrete colors, sort of, red or yellow or orange or green or blue, corresponding to, as you all may know, sort of oxygen or nitrogen or hydrogen. And we also see absorption spectra. So a source of, usually these are a continuous source with a cool gas in front. An example would be just the sun. The sun is a very hot continuum source with cool layers of gas on the outside that absorb light at those colors corresponding to different elements. It all comes down to quantum mechanics at the end of the day. So the amazing thing to me is the history of spectroscopy is scientists discerning all these different elements without any knowledge of quantum mechanics whatsoever. So we knew a whole lot about observing and understanding what was out there in the universe or even here on Earth before we knew anything about quantum mechanics. But the reason that we see light at discrete colors and wavelengths is because of the nature of the atom, that electrons are only allowed to be at really specific energies. And as they jump between those energies, they either absorb or emit energy at particular amounts, which correspond to different wavelengths of light. The reason I mention this is we don't have to get into tons of details about quantum mechanics, but understanding this allows us to know what things are made out of throughout the universe, right? That you can know what the sun's made out of or a gas cloud many millions of light years away. The fundamental physics is what lets us do that. So the flip side of that is for something like the sun, instead of atoms having electrons that get excited and emit light, they can actually absorb a photon and result in these sort of dark bands that you see in the sun or in another star. But I'm talking about galaxies, and the way that we actually do spectroscopy with telescopes. Astronomers have been doing this for well over 100 years. This isn't new. If you wanted to, you could actually, I should have brought them with me. If you've ever played with diffraction grating glasses or anything that can split light, that's a demonstration that we like to use at our open house. You can just hold a diffraction grating, something that splits the light, either in front of your telescope or at the eyepiece, and see the rainbows from everything in the field of view. This is an example of that, where you have a prism that's splitting the light from all of the stars in the field of view. And you could go and look at each of these little spectra and analyze the properties of the stars. You can see it's a bit of a problem, because if you split all the light, you end up with things overlapping. So like these two bright stars end up kind of smushed together. So if you want to carefully analyze the spectrum of one of those stars, you can go ahead and block out the rest of the field of view, and it would isolate the light from that star and really allow you to carefully analyze the spectrum of that star. And this is traditionally how we've done detailed spectroscopy, looked at the light from anything in space. This is still a technique that we use, actually, to mask the field of view of what the telescope is seeing, to only let the light through from the object that you want to look at, to be able to analyze the spectrum and see what it's made out of, how fast it's moving, how hot it is. The drawback is that you are throwing away information. It's the nature of the design of these instruments that you could only look at the sum of the light from a small piece of a galaxy, which isn't a problem if you're looking at stars. If you're going and looking at stars, you're looking at them one at a time usually. It might take time, but that's okay. But for galaxies, what that meant is you're throwing away information about what's happening in a spiral arm, or what's happening in this weird little region of gas that's colliding because of a merger. And over the last 30 years or so, starting in the 1990s, astronomers started to develop techniques to either collect information, collect the spectrum from many, many stars or pieces of a galaxy, or even better, to develop, astronomers developed instruments that could basically collect the spectrum from a whole galaxy at once and retain the spatial information. And there are two different ways of thinking about this. If you had a whole bunch of narrowband filters spanning the whole visible wavelength range, you could take a whole bunch of pictures and stack them together into a data cube and have, instead of just say blue and green and red, you could have 400 nanometers and 410 nanometers and 420 nanometers and so on and so on. And that would be really useful information that tells you something about what's happening in the gas and dust in that galaxy. Instead, we developed these tools called integral field spectrographs that collect a spectrum for each pixel in the image that you're looking at. So rather than a monochromatic image, when you look at the image, you can actually imagine each pixel in the image has a third dimension that has color information. So I have an example of that. There's one of these as one of these luminous infrared galaxies. It's an obscure galaxy. It's NGC 839. Don't worry too much about it. We picked it because it looked like it had one of these outflows that we were interested in studying. So just as an example, the Hubble Space Telescope image on the right shows you it's sort of a really beautiful high resolution disk with a little bit of dust. It's edge on. It's kind of like M82's smaller, more distant cousin. And we used an instrument called the Wide Field Spectrograph. The acronym is WIVES. But the image itself that you're seeing on the left, this is the same galaxy that you see on the right. It's very low spatial resolution, right? Each one of these pixels is incredibly large, but each pixel has extra information about the spectrum. Another way of thinking about that is if you take one of these pixels and drill into the screen, you can look at the intensity of light at each color. So you'd be able to see how much light is coming from oxygen 3 or hydrogen alpha or hydrogen beta, which for astronomers is really key because it allows you to measure really important quantities. It allows you to figure out how many stars are forming, how much dust is there, how hot the stars are, all of the really key physical quantities that we want to measure. So even though you throw away spatial resolution, you get a lot more information that's useful for understanding what's happening in the galaxy. So for something like hydrogen alpha, where you would, if you have a narrowband filter, you could take an image in hydrogen alpha and it would show you where all of the hydrogen alpha gas is. You could do a lot better with a telescope and a narrowband filter in terms of spatial resolution. But with an integral field spectrograph, you retain a lot of useful information. And I hope, let's see if this plays. So is there an animation going?
No, not yet.
Oh, bummer. So let's see if it works if I do this.
By the way, if you click on the upper right-hand part of your screen where it says format, I think that whole right-hand side will go away.
Thank you.
Thank you. Just letting you know.
Thank you. Appreciate it.
Oh, there's a play button on the upper. Oh, no, that's not going to work. The play button is just going to do the next slide.
Sorry, folks.
We saw the animation. You had it there.
Okay, good. So
there it is.
So
there
as
you go.
All right. So what you're seeing is a really low resolution image of the galaxy at different wavelengths of light of the hydrogen alpha line. So if you isolate the line and look at each one of these wavelengths, you actually get a different picture of the galaxy, and that's due to the gas being thrown out of the galaxy. You can actually carefully trace whether the gas is moving towards you or away from you, how fast it's moving. And all of that's really important if you want to measure sort of how much gas is being thrown out, how fast it's moving, how much energy is being thrown away. So even though we don't have the beautiful spatial resolution, you get a lot of extra information from the spectrum. One of the things I'm really interested in looking at is the sources of energy that are lighting up the gas in these galaxies. So when you look at a galaxy with if you look at one of these galaxies and you see an extended nebula of, say, hydrogen alpha gas, we would associate that with an outflow, a galactic wind, stuff being thrown out. But that gas can be sort of lit up by a number of different processes. It could be lit up by an AGN, an active galactic nucleus, and we're interested in hunting for those and understanding them. It can also be lit up due to a really intense starburst, light from hot young stars that's escaping out of the galaxy and just shining on the gas. And so we went looking for those two processes, and we saw something else. We saw that this nebular gas that's being tossed out, the image on the right is, again, sort of Hubble Space Telescope resolution. It's a bit more distant galaxy, so it doesn't look as beautiful as a nearby galaxy. But when we looked at the spectra, we saw that this gas was being lit up by shocks. The gas was being thrown out of the galaxy, and it was ramming into other gas and undergoing a shock. So you have gas that's thrown at other gas really quickly. It gets heated up as it does that, and it glows because of that. We didn't really expect to see that. It was unusual. We thought it would be lit up by stars or by one of these AGN. That is to say, it's something we weren't looking for, but we discovered that that was happening. And we saw that in a bunch of other galaxies as well. So we went and looked at a bunch of other galaxies with this technique in the hopes of looking for new stars that were being born, for AGN that were throwing the gas out, and then also for this shock process that seemed to indicate gas being thrown away. And the nitty gritty is it allowed us to do some calculations about how quickly you form stars, how quickly you get rid of the gas, and what will be the ultimate fate of galaxies undergoing this merging process. It also just looks really cool. So the problem is collecting these data are relatively time consuming. So over the course of a couple of years and about 15 nights of observing, we were able to collect, I think, about 30 galaxies worth of data. And what we tried to do was to understand the merger process, to look at what happens before you're merging, while you're merging, and then after you're done merging. We looked at galaxies, luminous infrared galaxies that were at different steps in the process. So we went and picked out galaxies that were really infrared luminous, but didn't seem to be merging. Things that were infrared luminous, but had started the merging process, and then things that were a bit mixed up and probably already done, and tried to see, do they look different? Do they look the same? We knew a little bit about how the star formation changed, but once we saw that there were lots of shocks happening, we didn't, like I said, we didn't expect to see that. We went and looked to see if this was happening in all these other galaxies as well, because we assumed that that was a tracer of gas being thrown out of the galaxy. And ultimately, what we found using this technique on a whole bunch of galaxies is that early on, you see at visible light wavelengths, you see lots and lots of young stars being formed. But as the galaxies merge, a couple of things happen. They make a lot of stars very quickly, which you see at infrared wavelengths, but the dust starts to obscure all of that star formation. So if you turn a regular telescope to look at one of these galaxies, it's really hard to see the star formation because it's buried behind dust. What you do see is a whole bunch of shocked nebular gas. So you see a lot of diffuse, just, many, many kiloparsecs of diffuse gas that's being lit up by shocks. And we think that's due to just literally gas running into each other and gas being thrown out. It was interesting. We're still trying to figure it out. But it was something we weren't really expecting. That said, I also wanted to mention another cool thing that you can do with Spectra, which is measuring the abundance of elements in these galaxies. So even in a galaxy, you can use a spectrum to figure out how much oxygen is there with respect to hydrogen or iron or different elements. This is really common for stars, right? Either the sun or any other star. If you want to know what they're made out of and what the relative abundances of those different elements are, you can look at a spectrum and look at the relative strengths of different lines. This is something you can do with gas in a distant galaxy. It's a bit tricky and not as accurate as looking at stellar spectra, but you can actually measure the abundance of oxygen across the face of a galaxy using a spectrum. So in general, we've known for decades that if you look at most sort of regular spiral galaxies, they tend to show a gradient, that they are much more abundant in oxygen, because that's what we're able to trace with these data. They're much more abundant in oxygen towards the center. And as you look towards the outskirts, the oxygen abundance decreases and decreases. We think that's a consequence of how galaxies are built, that the older parts are in the center. They've had more time to grow many generations of stars and cycle elements and build up lots of oxygen. And that the outskirts of galaxies are probably younger and haven't had as many generations of star formation and haven't had as much time to build up elements.
Jeff, quick interruption. So are you saying that if we're photographing galaxies, the type you're discussing, that instead of just dealing with LRGB, we should consider adding oxygen filters to this?
So for one of these galaxies, it's to measure the oxygen abundance, because you're competing with different quantum mechanical effects, you need a couple of different oxygen lines. So you have to be able to measure the temperature of the gas, the density of the gas, and to get the relative composition. So it's a bit tricky, but not impossible to do it with narrowband imaging. Typically, the three most important lines are a hydrogen line, a recombination line like hydrogen beta, oxygen 3, which is 5007, or 500 nanometers, and then there's a very faint. There are very faint forbidden lines, but there's also oxygen 2. So if you have oxygen 2 at 372 nanometers, oxygen 3 at 501 nanometers.
Yeah,
the relative strength of those oxygen lines allow you to suss out, with respect to hydrogen, sort of allow you to suss out how much oxygen is in the nebula that you're looking at.
So, but photographically, would that actually give us any benefit to just shooting RGB and L?
That's an interesting question. So I'm not experienced at all in terms of how it would look, like how O3 versus O2. That's how I think of it, the sort of the doubly or singly ionized oxygen, how it would look visibly. It would depend on the abundance. So for relatively low oxygen abundance galaxies, those lines are much stronger. So they would look probably a little more spectacular if you were to image them at those wavelengths.
It might. So in other words, it might be worth adding that to the shoot to see what you end up with.
Just to see, it'd be interesting. It's something I've never tried. Typically low abundance galaxies are going to be smaller, like dwarf galaxies. So something that's nearby but relatively small compared to one of these really big, massive things. And I should say, the reason that we went looking for this is other astronomers had observed this effect, a long time ago. They had looked at galaxies and measured the abundance of oxygen and noticed that there was this fall off if you look from the center to the outskirts. And it was predicted by people doing computer simulations that if you took two galaxies that had these gradients and threw them at each other, all that gas would get mixed up and you would lose that signature. It would just go away. I think this will play.
Wow.
This is this is a computer simulation that it's multiple different panels, but ultimately what someone did is took two galaxies in a computer, threw them at each other, and tried to measure as a function of position the relative abundance of different elements. And what they saw is the galaxy merger disturbs the gas so much due to tidal forces that this effect that we'd observed, this lots of oxygen in the middle and less oxygen in the outskirts, that it gets completely thrown out the window. It scrambles that signature. So it was one of these instances where this isn't always the case in observational astronomy, where there's a prediction and you can go see if it's true. But we tested this prediction. We went and looked for, in these galaxies that are merging, we went and looked for this signature being thrown out the window. As an example of that, I have a couple of plots, and forgive me, the plots on the y-axis are oxygen abundance. So the points that are higher have more oxygen, the points that are lower have less oxygen. Okay, from left to right is distance from the center of the galaxy. So for the galaxy on the left, it exhibits this property that we expected. The center of the galaxy here on the left has much more oxygen. The outskirts of the galaxy has much less oxygen. The purple line here is M83, a relatively nearby galaxy. The red line is, I think, Andromeda. You see a change, you see a gradient. And this panel on the right is the same measurement. So up is more oxygen, less, or down is less oxygen, left to right is from the center out. But this is one of those galaxies that's right in the middle of being merged, and the signal is completely gone. There's no more gradient. All the gas has been scrambled up and mixed up and sort of homogenized across the galaxy. What's interesting is we don't expect this effect to hang around very long. This is something that you would only see during the merging process. And then in about 1 billion years, it would very slowly go away as the gas gets redistributed. So again, in the lifetime of a galaxy, it's a relatively short-lived phenomena, but something that we were able to measure because we had a spectrum that we could use to make that measurement across the galaxy. So even though the images I was showing you of these beautiful merging galaxies, and then I showed you the integral field spectrograph with these big blocky pixels, you can get a lot of information out of it, even though it's low spatial resolution data. I think, as a reminder, here's an example of that. These are the, on the left is a Hubble Space Telescope image of the galaxy NGC 3256, that one from the very first slide. So Hubble images are great because they're the highest resolution you can get at wide fields. And on the right is hydrogen alpha light, so H alpha, with the wide field spectrograph. Pretty low resolution, but a lot of information packed into each one of those pixels. Because not only do you have hydrogen alpha, you have the intensity of light at all these different wavelengths, at these different colors. The data that I'm telling you about are actually quite old now. They were taken by the wide field spectrograph on a 2.3 meter telescope, which is pretty big. They were taken about 9-10 years ago. In the meantime, this technology has been developed further, refined, and put on larger telescopes. A really good example of that is the MUSE spectrograph on the one of the very large telescopes in Chile, run by the European Southern Observatory. So they pointed their spectrograph, their unique spectrograph, at this same galaxy, and their mirror is almost 4 times the diameter, and their quality of imaging is so much better that you go from this image on the right to something that looks like that. And just a reminder, this image on the right, each one of these pixels, which now it's harder for me to see the individual pixels. Each one of those pixels is a spectrum. So there's a third dimension you're not seeing that has the intensity of light at all those different wavelengths. The only way you can really get much better than that is with the Hubble Space Telescope, which for this galaxy NGC 3256, we actually did we were awarded time to look at this galaxy in more detail to try to pick apart what was going on. So if you were to image NGC 3256 with narrowband filters with the Hubble Space Telescope, you do a little better. You can resolve in great detail the star-forming regions and the gas. But just as a reminder, this was our starting point. So in 10 years, we've come a long way. And we haven't analyzed that data yet. Really interested to see what happens.
Well, once again, the resolution of the Hubble is actually relatively good.
Mm-hmm.
Just an issue, I think, of post-processing and doing HDR, because you can control the intensity level on the Hubble, correct?
Yeah, and it depends on what you're looking at and how you're looking at it. One of the problems with these telescopes are these objects are relatively distant. So the actual spatial resolution of these images for the very large telescope, for the image in the middle, ground-based imaging limits us to about 0.3 arc seconds per pixel to maintain the spectral information, to actually maintain the
Okay.
So you can do better, but you lose the spectrum. And on top of that, the other way around that is adaptive optics, which is something that is happening. So we're with these professional telescopes and integral field spectroscopy, we're battling the atmosphere. That's our problem. Now, the Very Large Telescope with this.
Holy crap!
So there should be a space there. That's okay.
Oh
Wait.
no, it worked. Oh yeah, that worked.
So this is an example of an integral field spectrograph being pointed at Neptune, right? The regular ground-based data is seeing limited, so 0.3, 0.4 arc seconds per or so. With adaptive optics, with this technology that corrects for the distortion of the atmosphere, we're getting to the point where we can do as good or better than the Hubble Space Telescope from the ground. In limited cases, in certain circumstances, smaller field of view. But it's amazing to me that, so we're looking at Neptune here with a adaptive optics aided spectrograph. You can actually do slightly better than the Hubble Space Telescope. This is from a press release that the European Southern Observatory gave a couple years ago. That ground-based adaptive optics is getting you to the precipice of beating space-based telescope, much smaller, but and in the future we'll have bigger telescopes with even better adaptive optics that can cover wider fields of view. So in the next 10 years, you're going to start seeing really highly resolved data that allows you to drill down and see what we couldn't possibly see before. And
wow.
I sort of heard,
quick dumb question. For those of us that actually don't care about planetary and just do deep space objects for art, does that affect us as well? I mean, or do I don't ever have to worry about that because I'm doing DSOs?
You mean adaptive optics?
Yeah.
Adaptive optics typically require sort of really sophisticated electronics and technology. So you're much better. I'm not an astrophotographer. There's probably lots of people on this call who know way more about this than I do, but there are other techniques that you can do to battle the atmosphere with that you can't do with big telescopes because of wanting to maintain the spectral information versus the image.
Okay. Yeah, that works. Thanks.
And I wanted to take a detour into some of the other future of using this integral field spectroscopy technology. There are surveys that are mapping thousands of galaxies using this technique that have already happened. So in the course of my work over a few years, I was able to look at, I said, about 30 galaxies. In the last 6 years, 2 surveys have been able to use this technique to look at about 20,000 galaxies, just with hundreds of people working together. And any one of the people working on that project could give a whole bunch of talks about all the interesting things they've learned about galaxies. And all of these data are public for folks who want to go and study it and figure out what's happening inside of galaxies. Another interesting thing is a lot of these instruments are very tricky to build and have very narrow fields of view. They might only be looking at an arc minute on the sky, something really tiny. In the last few years, we've looked at developing techniques that allow us to map really big nearby galaxies. So this is an example of a relatively large data cube where we don't just have an image, we have a spectrum at every point for something that's almost a third of a degree on a side. We couldn't do that with the cameras that we had before, but the Sloan Digital Sky Survey, which is this massive survey that uses new instrumentation every few years, they're building new instruments right now to try to map the nearest galaxies in great detail, to look at the star formation, to look at the gas, to look at the elements, everything that's happening in those galaxies and in those clouds. So this hasn't happened yet. We're building the spectrographs and the telescopes to do this, but they're going to map Andromeda, the Magellanic Clouds, as well as big nebular complexes in the Milky Way, to dig down into the physics. The images won't be as beautiful, but the information and the data will be phenomenal. So probably in about 6 or 7 years, someone from Carnegie can come give a talk about this. But I just wanted to give a shout out to Luminous Infrared Galaxies again, because I did say I was going to talk about those, because that's what I like to study. And I wanted to highlight, so this week is the American Astronomical Society's meeting. There are lots of folks presenting whatever the most interesting results that are happening from their work. There's actually a lot you can learn from these galaxies. Because they're mergers, because they're undergoing transformative processes, folks have pointed all kinds of telescopes at these things to try to understand how stars are made, how galaxies change, how you grow supermassive black holes. It's not a coincidence that a lot of these galaxies were observed by Chip Arp, because they're peculiar and weird, and they're peculiar and weird because they're interesting, that something interesting is happening to them. And just as a couple of examples, there are a couple of astronomers, Anne was in California, she's not anymore, who are using these galaxies to study how you grow a supermassive black hole. So we know that most galaxies have a supermassive black hole. The bigger the galaxy, the bigger the supermassive black hole. You can take other instruments and drill down on the centers of these galaxies and look at what's happening with the supermassive black hole. So these astronomers used an instrument on the Keck telescopes that looked at a tiny field of view, only a few arc seconds across, to look at what the gas is doing right at the center of these galaxies. They've looked at a whole bunch of them and they're still processing the data. But they found evidence that as the galaxy merger happens, you end up, what you expect would happen happens. The supermassive black holes merge and you end up with an even bigger supermassive black hole. There's another astronomer in Pasadena who's measuring how you make stars in these galaxies. So not the gas and dust, but the stars that are being built themselves. And what she found is that these luminous infrared galaxies, not only are they making stars 10 to 100 times faster than the Milky Way, they're making star clusters that are way bigger than anything you would expect in the Milky Way. That you're building these incredibly massive clumps of stars that actually look a lot like what's happening in very distant galaxies in the early universe. We don't know why yet, but we observed that in these nearby galaxies. We're still figuring that out. A corollary to that is using even the broadband Hubble Space Telescope data. Even if all you have is a B and an I image, the color information, the difference in blue versus red, tells you something about the age of the stars that you're looking at. Another astronomer looked at these Hubble Space Telescope images and measured how old the star clusters were and found a whole bunch of really young, massive star clusters, something that will be a bunch of globular clusters left over in about 1 billion years. All of these processes are interesting, but they feed into the bigger picture of understanding how you end up with something like the Milky Way that has a number of globular clusters, yada, yada, yada. And you get to look at a lot of really cool data in the meantime. And just finally, I wanted to mention...
Jeff, Real quick, can you zoom out to 100% on the top left corner of your screen? Yeah. Thank you. Some was getting cropped off.
Oh, let's try that. Does that work?
Yeah, the problem is the side screens are still there, so 100% doesn't work. It's cropping your screen. That's better.
Okay. I just wanted to quickly mention that we're hoping to look at all of these interesting merging galaxies with the James Webb Space Telescope. It's currently scheduled to launch next Halloween, this Halloween, if everything goes okay. These galaxies have, because they have a lot going on, lots of different telescopes have been pointed at them. We've looked at them with the Spitzer Space Telescope, which looks at mid-infrared wavelengths of light that can actually penetrate dust and see what's happening behind and underneath the dust. And I included this image on the right just to show a comparison of the resolution of the Spitzer Space Telescope, which was the best cutting edge infrared telescope, more or less, that's been available to us. The image in the middle is an image of the field on the left that was taken with the Hubble Space Telescope. And the image on the right is a simulated picture of how that field would look with the James Webb Space Telescope. So JWST, the advantage is the resolution and the wavelength of light. That combination has never been seen before. We have a program that will look at a couple of these galaxies with JWST once it's launched, and all of that data will be made public for everyone to look at immediately to see what the heck is going on. And this is an instance where I think, because it's technology that hasn't existed before, we have expectations, what we think we might see, but I'm really interested to just take a look and see what we don't know, what we won't expect. So the fun part with any new amazing technology is when you point it at the sky, you have some expectation of what you might see, but usually the most exciting things are what you didn't expect in the first place. So I'm going to end on that note because I've already talked too long anyway.
Hey, Jeff, quick question, and this is probably sort of stupid because I am not an astronomer. I'm a photographer. So my stuff is about art. You'll see the picture behind me and realize, oh, that's not real. I don't care about real. I care about pretty. You spent a lot of time tonight talking about infrared. And if I'm not mistaken, outside of my narrowband filters and all that, if I'm shooting luminance, it's got an infrared filter. The whole point to my photography is to eliminate infrared. And that's, by the way, that's an ignorant statement because I don't actually know why I have an infrared filter. Your turn.
That's not atypical for digital cameras on the ground because you don't when you're taking a picture, you don't want light that is not visible light because it's not a good representation of what you'd be seeing anyway. And so a lot of consumer cameras have a filter cutoff that gets rid of.
Oh, I'll interrupt. I have an Astro camera and I run filters. So in other words, when I'm shooting a monochrome camera and I have a filter for hydrogen alpha. I have a filter for oxygen, sulfur, red, blue, green, and lume. The luminance filter is an IR blocking filter.
Okay. In the case of astrophotography, someone else might be able to answer better. I know
The
that
reason you have the infrared block is especially if you have a refractor.
Yep.
The infrared light is typically focused very badly compared with the portion that's in the visible spectrum. So you want to block that so you don't fuzzy up your image.
Okay, so that gives me the sharper stars. So, but that means that everything that Jeff was talking about shooting earlier, I probably can't grab because I'm specifically working with minimal wavelengths. and none of them allow for infrared.
The other thing is you're using a silicon sensor, and the range of available infrared sensitivity cuts off at about 1100 nanometers.
Yeah.
And what Jeff is doing is much longer wavelength than that.
Got it. Okay, because he was talking, Jeff, sorry, Jeff, you were talking about infrared a lot, and it was most of my education to this point was eliminate infrared. And so I was trying really hard to figure out how to incorporate your stuff into my stuff.
That's fair enough.
Jeff, a quick question, Dave Yackerson here. I got to see the James Webb Telescope up close. And my question to you is that's been going on for years now, that they've been working on trying to get that in outer space. Are they upgrading anything from getting information from you as an astronomer or the other astronomers that you work with? That are they going to upgrade the systems that are in there, or are they keeping the old stuff that's been like a year or 2 or 3 years old, I guess, on that? Would you know?
Anything that's on the telescope, any flight hardware is not going to change, to my understanding. I haven't worked on a space mission, but the folks that I know who have to have space ready hardware, it's usually going to be behind the curve in terms of tech, just to get it up in the air. And there could be people here who know about that because they've worked in that. Like I have folks who've worked on that sort of thing, know that inside and out. The big focus from the folks who run the telescope, who are going to run the telescope, and from the astronomers, has been data processing, trying to figure out how can we make the software better, how can we process the data better. We know we have these cameras, so what can we do to get the most out of the data as quickly as possible, especially since the telescope's nominal mission is 5 years. So we want to have as much information in the community as quickly as possible so that we can make the best use of what is on the telescope.
I just want to say thank you so much. I'm very impressive, your talk, and you're so knowledgeable about what you do. I really appreciate you being here. Thank you.
Thank you.
Yeah, I'd like to throw that in as well. This was one of the most informative discussions I've ever had.
Appreciate it.
Mr. Rich, I have a question.
Go ahead.
This is referencing a slide much earlier in your presentation where you compared the emission spectrum from hot gases compared with the absorption spectrum associated with colder gases. If star formation, you were saying, begins with cold condensed gas, and we talk about M42, the Orion Nebula is described as being an emission nebula, does that mean star formation is occurring within just pockets of cold gas within M42? Is the area around the trapezium stars like a colder gas area?
That's a really good question. I mean, that's a good example of how when you have the ability to resolve what's happening. So in Orion, you can see the young hot. So trapezium, those are young hot stars, and they're actually putting off so much radiation that it's pushing the gas away from those stars and forming a region of hot ionized gas around them. And when that happens, the gas that's near those stars can't cool and collapse and make new stars. So the actual young stars are going to be born somewhere where you have a dense cloud of gas that can cool and form molecular gas. And so in a single star forming region, you'll see absolutely what you said, a mix of pockets of cool, dense gas and hot gas where the young stars have gotten hot enough to push things away and form a region of ionized gas. And when you look at a distant galaxy, you're smearing over all of that because you just don't have the ability to resolve it. The physics is the same, we just can't see the details.
So being so much closer, with Spitzer or the James Webb Telescope, are you able to predict where like new star forming regions within M42 would be?
So that's also a really good question. There's been, I don't think I included a slide in this talk, but one thing that I love to show when we're talking about the difference between visible and infrared light is these really local star forming regions, because you can, if you have an infrared telescope, it can actually penetrate the dust. So I went back to the slide with the pillars of creation where the star formation is usually happening in these dusty, at visible wavelengths. It's going to be dusty, and so you can't see through to where the young stars are being born. But with something like the Spitzer Space Telescope that sees longer wavelengths of light, it was able to, that and other telescopes have been able to take pictures of the young embedded stars as they're being born or before they're born.
Are you able to specify where in the spectrum, in the IR spectrum, you're seeing that? Like how far, what wavelength, like what nanometer range are you observing to get through the dust in that situation?
It would be relative. It would be longer, but not too long. It's tricky because the dust itself will start to glow at longer wavelengths, like so microns. So 1 micron would be 1,000 nanometers. You would be looking at sort of 3,500 nanometers or 3.6 microns to be looking through the dust and see relatively young, relatively warm or hot stars, but not the dust itself glowing at say those wavelengths. As an example.
Okay, thanks. That's a great answer. Thank you.
Okay, Jeff, thank you for your presentation. We thought it was very good. Excellent presentation. I learned a lot from it. I think all of our members of the club appreciate you coming online to do that. Any other members that would like to stick around after we adjourn the meeting to ask questions and interact with Jeff, you're welcome to do so. We do need to get on to the rest of our presentations we need to do for the meeting. And of course, the next item on the agenda is the door prizes. Alicia, are you there? Is Alicia still here?
I haven't seen Alicia on, but
okay, looks like Spencer, you do the door prizes.
okay, so I just sent out a link. Last chance to register. I'll give you 30 seconds to get registered before I close it out.
Seconds.
Hurry up.
I'm going to jump in for a second and say, hey, thanks, Jeff. That was actually brilliant. Understand, I'm an artist. I'm a photographer. I'm not an astronomer. Everything you talk about, I'm learning inch by inch. And that was the most enjoyable technical conversation I have heard in 2 years.
Hey, Jeff, Jeff, do you guys, you astronomers that, do you have a conclave at the end of the year to where you put all your information that you've learned together and can combine what you've learned, or?
We try to tell folks as it's coming in, and then, you know, I always pitch the open house because it's a good time to connect with people and ask those questions. Otherwise, it's just an ongoing process. The big meeting that's happening right now virtually is an example of one of the biggest meetings that we have in the US where folks get together.
Oh, that's great. Awesome.
Yeah, here's Jack out here in High Country, Colorado. And Jeff, I want to say that was a tremendous presentation. You get both thumbs up.
Yep.
And very informative, and I've over my career have worked on some of those instruments, the Fourier transform spectrometers and such, and kind of can sympathize with trying to get data out of those things.
So you guys are going to laugh at me.
One.
You guys are going to laugh because any of you that know me know I am not the astronomer. Okay, I'm the new guy that's been taking pictures for a couple of years. So I got photographed and interviewed today for an article in Peninsula magazine for the Rancho Palos Verdes Peninsula. I hope I didn't embarrass anybody. I did put this hat on at one point, so there are a few pictures of me talking about LAAS. I have no clue what they're going to write or how they're going to do it, but somebody saw my stupid pictures and thought they were cool, and so I'm going to be a highlight next month in the magazine, and I hope I don't embarrass anybody.
Thank you, Richard. We don't think you will.
Okay, well, the comment I wanted to make about Jack, I think I don't know if he is a longer member of LAAS than Tim Thompson or Dave Sovereign, but I know Jack has been around for an awful long time. Okay.
All right, so let's, I think we're ready for the
I think we
drawing.
need to go to the door prizes.
Yeah, okay, so, all right, let me share a screen here. Daryl, can you take notes so that I don't screw this up? So basically we have three sets of prizes. We have 2 Amazon gift cards for $25. We have your choice of anything on the LAS website, and we have hats. So we have 2 Amazon gift cards, 2 choices from the website, and 2 hats. So I'm just going to go Amazon website hats, Amazon website hats. So so I've taken the names and I've copied them into a spreadsheet. And so the first prize is for Dan Vernansky. So he gets the Amazon gift card.
Can you share your screen, Spencer?
Oh, I'm sorry.
We trust you.
Okay.
Go ahead, Spencer.
All right. Okay. So that's the first one. All right. So let's see. Let me take his name off of here. Okay. The next one is Andrew Inohara. He gets his choice of what's on the merchandise part of the website. Okay, and let's see, let me take his name off of here. Okay. And Casimir gets a hat. Okay, Kaz gets a hat. Okay.
And son.
Yep.
All right, let's see. Where's his name here? Let me find it and take it off of here. Oh, here we go. Okay. Martin gets an Amazon gift card.
Nice.
Hey, Martin.
No, wrong Martin. Down.
All right. Goody. Thanks.
Right. Wrong Martin. Right. Sorry.
row 26, Spencer.
Okay. All right. See, I told you I was going to screw it up.
Out back.
Okay. So Babak gets the website.
Cool.
Okay. And let's see. Let me take him off. Okay. And the other Michael Martin gets the hat. Okay, that's it.
Ooh.
So normally Alicia would be getting in touch with you with the details of the gift card and and what's on the website, and we'll get your email address and your address, and we'll mail the hats out to you. Okay, that's it.
Okay. It looks like we had a fairly good turnout. What was the maximum turnout we had tonight, Spencer, on the Zoom meeting tonight?
41.
41.
41.
Not bad at all. We did pretty good.
So a couple of things. One,
yes.
Nasser had a technical problem with some of his slides, some of his photographs last time. And so he asked if he could represent some of them. So I told him at the end of the meeting, after we've adjourned, he's welcome to share the images that he couldn't show. And then of course, I'll keep the Zoom session open for a little while longer because I know people love to socialize afterwards.
Well, I always like to see Nasser's images.
Is Nasser here?
Pardon?
Is Nasser here? I didn't see him.
He was
he's
here.
here. Yeah, he's here. He's got the green sky.
Okay.
Okay, so I'm gonna stop the share. So
I'm just going to throw this out here again and say, Jeff, thank you very much. That was really, really awesome.
Yes, thank you very much, Jeff. Appreciate it.
Okay,
Yeah,
thanks a lot, Jeff.
Jack out here again. Thank you, Jeff. Excellent performance.
Oh, okay, guys. I think it's time to adjourn the meeting then. And if Nasser's still around, we can look at what his images are and that he couldn't do last time with technical difficulties. But I'll go ahead and officially adjourn the meeting. And for those, we don't think we need seconds on this one.
I know, I'm playing with it. Now that I'm on the board, I figured I'd have some fun with it.
I'll just go ahead and pound the meeting closed. And for those who want to leave, go ahead. And those who want to stick around, go right ahead. Okay? Okay, the meeting's officially over.
Hey, Joe, I'd like to get your phone number if that's okay, or privately, or
Okay,
Put it in the
I guess
chat.
I can share the screen.
Okay, go ahead.
So, no, yeah, what happened last time was I was sharing the wrong screen basically. So what everybody saw was a very like a 25% of the screen. I mean, it was not in a full screen mode. So images were tiny. I don't know if anybody noticed that, but nobody alerted me. And then when I saw on the YouTube, I said, oh, wow, oh, that's not so good. So maybe I can do it again. So yeah. Okay, yeah. Let me share the screen first, I guess.
Yeah, I know. I was thinking that myself. It's a big yawn. Sorry.
Now,
oh, nice.
Do you guys see the bigger screen or smaller screen? Just want to make sure.
Large.
So why did you go monochrome on this? It's brilliant, but why did you go monochrome on this?
So are you guys seeing the bigger screen, right?
Yes, Nasser.
Yeah, so far.
Yes, it's a full screen.
So anyway, yeah, I've imaged a lot of photographs, many of them in color, but most from backyard, since I do it in narrow bands, and obviously H alpha is the most strongest. So
that shows off the horse
a lot
head
of
really,
images
really
in just
well.
H alpha. And to get the color, I have to do a lot more imaging. So
Nasir, is that
The horse head.
hydrogen alpha or LRGB? Which filter is that?
This horse head is H alpha only. This one.
That's awesome. I'm going to do that. I'm going to do that tomorrow. I love it.
But the one behind me and my background, that's H alpha O3 and S2. Basically,
Well,
that's I think.
But that's Hubble palette, right?
Right.
Yeah. But no, I'm Hubble palette all the way. You know me. I'm not about real. I'm about art. That shot that you have up on your screen is freaking brilliant.
Okay, so I just wanted to show you. I'm sure some of them saw it last time, but I basically imaged from bottle 8-9 skies. This is in Lake Balboa in the valley. And it's pretty bad, but still with narrowband, I mean, you can get pretty decent results. And the stuff that I use is 80 millimeter stellar view telescopes, iocron mount, which is still Vance around here. I still using his mount, and it's doing pretty good job. And the camera is 16 millimeter and LRGB filters that I use, and 3 narrowbands. This is the PixInsight screenshot that I use for software processing. And so, okay. I just want to scroll through quickly. Some of the objects that the solar system is pretty easy one from the backyard. So this is Mars did of occultation by the moon. And this was the comet that came last year. It was done from my backyard.
Wait, is that the first one or the second one?
This one?
Yeah.
Neowise. Neowise right there.
Yeah, that's the first one. Okay, the second one was Atlas?
This is Comet Neowise. Yeah, there's the most, the famous one.
Yeah.
Others were not so.
Yeah,
the others were faint.
Quite as pretty. Yeah, okay.
Yeah, the others were faint.
Yeah. And of course,
Oh,
this was the Saturn Jupiter. Of course, I did some more imaging after that, but this is before the conjunction. Yeah. When they were actually, this was like 1.5 degrees apart.
Nice.
This was Neptune, that being pretty close to Venus. Venus
That's
and
really cool.
Hades.
Yeah, that's really cool. I like that a lot.
Oh, I didn't get.
Then
I
these
get.
are
I didn't do that
easy,
one.
easy to take from a backyard. This is from the backyard. Actually, you can see this is a tiny galaxy, which is 500 million light years away. And this is about 200 million light years away. So this is one of my best shot of M13.
Yeah, but it's not a colliding galaxy.
Yeah, one of the things I kind of wanted to ask Jeff a question. He said he was talking about colliding galaxies, and he was talking about Milky Way and Andromeda. But wait a minute, that's us.
They're going to collide eventually, like in
Yeah.
4 billion years.
Yes.
Right, but okay, so they're going to collide. But what does that do to us? I
We're
mean,
dead.
Nothing.
We will
we'll
be dead.
gone by then. I get that.
Nothing. The space between the stars is so great. They pass one another. The only thing that will collide in each galaxy is probably dust clouds and gas clouds. What
It
it'll
will be
do
in
to the
such a
stars,
slow motion
what it'll do
that
to the
nobody will
stars,
notice
it'll
it.
gravitationally scatter them.
Okay, no, but that
So
was the
they don't
part I
start
didn't
collisions.
understand. That was the part I didn't understand. It's like, okay, when galaxies collide, way in the smaller scale of things, there's little planets in there. They're not affected.
No.
Right. Okay, that was what I was trying to figure out. That because I really don't know anything about any of this. Sorry, Nasir, get back to work.
Yeah.
Oh, that's nice.
This is from my actual backyard. This is just H alpha and red filter. Yeah, it's about 60 minutes.
Nasir, what did you use to shoot that? Because Andromeda is too big for most of us, even at wide field.
No, it's ZWO 1600 is
no, but are you shooting an 80 millimeter
80 millimeter 560 f7? So it's just about the right size for the Andromeda.
Okay, because for me, I mean, with my reducer, I have trouble fitting it. So yeah, you did good.
You have to look at your sensor size and the field of view.
Remember, it's over 2 degrees wide.
No, my point is my scope is about 2 degrees. And I know that
yeah, this is about 2 degrees by
that's what I thought.
Approximately.
Yeah.
But this is already cropped a little bit.
Yeah, you already cropped off at least one end.
Yeah.
I guess, yeah, I think that's probably for most of us, that's probably a mosaic shot.
This one I just tried.
That's the Leo triplet.
Oh, okay, so that's Bode's, right?
Galaxies are no good. I mean, you have to go to Lockwood for Galaxies, but this is something I just
You should
tried.
see the
Leo.
The Raza is pretty wide field. I mean, you can fit a lot of the Andromeda without even, and you still have space around it. It's pretty impressive actually how wide that is.
Yeah.
So nebulas are obviously the best spot to do narrowband in from backyard.
Najir, the shot before the Galaxy, was that the Bode's Galaxy?
That's the cone.
Excuse me?
David, say that again?
No, I'm commenting on his current photograph. That's the cone.
Yeah.
Oh, yeah, no, I'm talking about the one before. Was that the Bode's Galaxy?
Yes.
Right.
Yes, I saw it.
Okay, so that's Bode's. I've never been able to figure that one out or shoot it. I got to work on that maybe this next year. Oh, okay. Forgot its name. Crescent. Yep.
Yeah.
You should call that the jellyfish.
1 hour of H alpha.
Horse.
That's
No.
about 2
Tadpole.
hours of elephant.
Oh, that's right.
Trunk.
I couldn't
Oh,
figure that
elephant.
one out.
Yeah.
This is the trunk.
That's the elephant.
Yeah. So once again, on some of these you're doing color, and some of these you're just doing black and white. Is that?
Yeah, because in H alpha it's easier to image, and then, I mean, it's an ongoing project, and so I will probably add some more O3 and S2 on this and get some colors on it.
I'm not picking on you. I'm just questioning what
This
you're
is,
shooting because I want to learn.
Yeah.
I shot this shot, the heart, and I hate my picture because it's just all red.
Yeah,
So
I can turn this into red. I can turn this into red. Single
I like
color,
yours
but
better.
Monochrome looks better.
No, but remember, he's Bortle 8, Bortle 9. That basically means if you're lucky, you'll see first mag stars. So a lot of the stuff, hydrogen alpha is not predominant in light pollution, which tends more toward the yellow, where it peaks. And with these new LED lights, God knows where it'll peak. But that's why I can understand. That's why most of these are H alpha, because H alpha, that wavelength doesn't come through that bad in light pollution.
No,
all the other wavelengths are
I-
out to lunch.
See, I have a weird ass advantage is that I'm literally on the ocean. So anytime I'm shooting to the south, I don't have any light pollution. So I know
Yeah,
that
well, Nazir does. So do I.
well, so that sounds stupid because even though I live in Los Angeles, 75% of my images don't have light pollution. So my Bortle changes a lot. But I still question all of these things because I'm still trying to learn it and figure it out. By the way, that's
catching
awesome rosette.
That you catch last two or three emission nebula, Nazir, you're catching these dark lanes very nicely. They're very well defined.
Yeah, I mean, yeah.
I love it.
Rosette comes out pretty good in H alpha, and then a little bit of you throw in O3.
I love those dark lanes.
Phil, when we get to Vesperas, will it look anything like that, or
this is just H alpha 30 minutes.
Oh
just
yeah,
30 minutes.
That's where that's where you're picking up those dark lanes. Yep.
This is actually a really good example of comparing the IR sensitivity of the cameras available to us going to like 1,000 or so nanometers wavelength, and what our guest was talking about with Spitzer and James Webb going to like 3,500 nanometers and longer. That these NASA's images are able to penetrate that light pollution and a lot of dirt in our own atmosphere, but we're still seeing the dust lanes so clearly in these objects, which the Spitzer would penetrate.
Yeah, great.
Yeah, it's different sensors. Remember, CMOS and CCDs don't go that deep. Don't go that deep into the infrared. They go into what we call the near infrared, the shorter wavelengths. But the far infrared, which are the longer wavelengths, which penetrates all this stuff, you need different technology for that.
Yeah.
All right, Nazir, you're gonna have to.
Space.
Yeah. Nazir, you're gonna have to refresh my
You
memory.
can't
What's that
filter
open
what you
cluster at the
don't
bottom?
have, right?
Yeah.
You can't
What's that open
filter
cluster?
what you don't have.
David, you said something?
Yeah, what's that open cluster at the bottom there? I forgot.
It's M52.
Oh, that's right. That's that because there's the bubble nebula right
that's
there.
really
Oh, that's
cool.
right. Sorry,
David
me
knows that
bad.
stuff.
I should have realized that. Me bad.
You can read. You can. I suppose.
No, I can't see. I can't see the rest of that because it gets clipped by this other thing. I'm trying to figure out what to do
Oh,
about
I
that.
see. Okay. I hope I am not clipping it.
No. Oh, I see what I'm doing wrong. Okay.
This year, you're good. We see everything. Yeah. Oh, California.
Yeah, this is one of another favorite, easy one to do in H alpha.
Hey, Nazir, did you use an unsharp filter on this?
Which filter?
Unsharp.
It looks a little over sharpened.
The reason why is because there's a dark halo around all the stars.
Yeah.
that are in front of the nebula.
That happens with when I try to do deconvolution in PixInsight. Sometimes it happens. So I'm not good in using that process very well yet. So
Okay.
It
All right.
creates this halo
Looks like
sometimes.
unsharp filtering, but it's not. Okay.
Yeah, it tries to sharpen it, but sometimes it just overdoes it.
Nasir, which scope did you use to shoot the bubble?
They're all being I just have one telescope.
I forgot what scope you're using. Are you
80 millimeter Stellaview.
It's the same as me. Okay. Because I shot the bubble this last month or so. I haven't processed it yet. So I'm the idiot that, I know I've taken the pictures, but it'll take me 3 months to actually take the data and make a picture.
Done with, I think, single one-shot color camera, ZW294.
Yeah, you could see the light pollution starting to leak through.
I
this one.
know I could shoot that.
Yeah.
Wow.
Yeah, the whole star field is got a glow behind it. Yeah, it's star rich, but it would have been darker if one of the
Oh,
one of
that's
the filtered images we
Yeah,
didn't use.
David, that's
color,
totally fixable.
get
That's totally fixable. You just reduce the star size, use StarNet to get rid of them, bring them back later. But I didn't know I could actually get the dumbbell that big in the screen with my scope. Holy crap. Thanks. No, seriously, Najir, I had no idea. That's awesome.
That's another,
Okay.
I think it's just 20 minutes. Yeah, now it's too late in the season now to get some more colors into it,
Yeah.
but maybe I have to wait next year.
Now, Najir, this is the helix. I know the helix is much larger than the dumbbell. So on the previous image, did you crop it?
Oh yeah, these are cropped. Yeah, this one is
They're all
cropped.
cropped. That's
pretty
cropped.
much,
I
and
thought
this
so.
is also cropped. Yeah.
Yeah.
These are tiny.
Ah, okay.
Yeah, you could tell by the star sizes.
Right. Yeah.
You can tell by the star sizes. Let's look at the large star sizes here.
Yeah, okay, that makes more sense.
Yeah. Nice helix though. You got one of the outer rims
Yeah.
poking through. Yeah.
I can't believe this
Whoa.
is only 20 minutes of H alpha.
Did you get nailed by a satellite or a meteor? Look at that streak.
Yeah, it's a meteor.
Yeah.
Yeah. I think. Oh, is that a meteor? Okay. I thought
Gotta
maybe
be.
one of those
I don't know,
pesky
yeah,
starlings.
that's probably a meteor or something.
Okay.
It's random brightness, so it makes it more likely it's a meteor.
Oh, that's right. That's right.
It's not
Richard's
a
right.
straight line.
This is
Which is
no
right.
good. You need a lot more focal length for this.
Oh, the ring. Yeah. I've given up on the ring because only my Maksudov can pull it in with enough magnification, and then the life stack doesn't work. Not enough stars.
Yeah, I've done this zillion times. This object,
So has everybody.
but this is I just tried like 16 minutes of H alpha 03 from my backyard, and turned out really not so bad. So,
Yeah, it's not so bad. I mean, Vance will tell you we've tried that again and again at Garvey Ranch. We finally got one that I'm satisfied with, but you just got to keep working at it.
By the way, Nasir,
Again, darkness.
all of my local images, like
Wow.
Orion, etc., I am now I'm not shooting anything less than 50 hours.
Wow.
You
Look at the
guys-
dark lanes. Look at those dark lanes. That usually never shows up.
That's nice.
Look
this
at
is
that
just H
texture.
alpha with a little tint, so it's got a little reddish.
Oh,
tint
yeah.
on it.
But usually these dark lanes in the main part of the continent, you never see. They always overexpose it or something. So this is H alpha alone, right?
Right,
No,
but
that's
just 1 hour of
hydrogen
H alpha.
right? Yeah, that's hydrogen alpha. That's
Wow.
really nice.
Yeah,
That
it's
is very nice.
Beautiful.
I
Nazir.
like that. Ah. Yeah. Yeah.
This is also one of the
Yeah.
M8 from.
Well, look at the dark lanes, the dark patches around the bright core, the right there. Wow. That's amazing.
That's great.
Very amazing.
That's an interesting shot. Oh,
Terrific.
on your nebula, on your lagoon, it was
Huh.
interesting that there's not a whole lot of transition between that center circle and outward. It stays yellow, green, and then finally ends. I found a lot more dispersion between that middle and the sides. That's interesting.
Yeah, this is Hubble palette, so I guess you get.
Yeah, that helps.
Well, no, I did
With
I
Orion.
did Hubble on mine too, but I'm just surprised that there's not more differential to the left side.
I think the lagoon's that way. I photographed that multiple times. It's just tricky. It's tricky to get the finer details and not but expose the outer regions.
There's a lot of
you know.
blue around here.
Yeah.
I've never shot this one. Is that a big crop or is that a small one for my scope or?
No, the stars are small, so my guess is a medium crop.
Yeah, it's a medium crop,
Yeah.
not too much.
What
I mean,
time of year did you shoot that?
This is all early evening. I mean,
No, no. I mean, is this a winter target?
No. This is Sagittarius.
Summer.
No, this was like,
Summer.
I think September,
No,
October.
no, that's what I mean. So it's gone now. I can't do it now.
Yeah, it's gone.
No. This is Sagittarius. This is long gone.
Okay.
Yeah.
No, but my point being is that's pretty cool. I would like to shoot that.
This one
winter.
again, too much sharpening here. So
Yeah.
some more work on this.
Yeah, you gotta back it off. So the stars, the big thing is the stars all have dark halos around. It's really prominent around the nebula. You just have to back that off just a little bit. But again, love the dark lanes. Look at that texture in there.
That's gorgeous. That's gorgeous.
Oh my God, that is amazing.
This
here again.
Turned out to be pretty good.
Yeah, pillars of creation.
Yep.
It's an almost 3D effect on that. That's just really phenomenal.
Yeah.
So, Nasir, I got to ask you, all of your shots seem to be an hour, 2 hours, 3 hours.
Yeah, because I'm lazy. I don't.
No, he's auto guiding, right?
Oh, okay, all right. Because my whole point was, there's not that many targets.
I think my record, probably this is 4 hours, is probably a record. I don't think I've done any image more than 4 hours.
Now you're auto guiding, right, Nasir?
Yeah.
That's why you could walk away, and as long as the computer doesn't barf, the auto guider will take care of everything. I've had that experience.
David, I do the same thing. The point is, I shoot the same target for 4 or 5 or 6 weeks. I make sure I get 50 or 60 hours on a target. That's the only reason I'm asking. I'm not picking on anybody. I'm just asking because
my own experience, and I don't have an auto guider, so I have to live stack. So I'm limited with my individual exposures, but I've run numerous tests. And my own feeling is that if you look at the histogram for the individual exposures, and you can know where the background is. Once the background is in the middle, you're basically losing dynamic range at the high end. So you gotta keep that big hump more or less to the left side of the histogram, because otherwise you lose dynamic range. You're actually oversaturating. That's my experience.
I just wanted to show you some more similar photos that I actually this year try to make a calendar out of this. And maybe if I get it printed out, maybe I'll pass one on for door prizes.
Yeah, that's freaking
cool.
Nasir, your shots this year were brilliant. You really kicked ass.
Nasir, I've been watching your stuff. You really come a long way. They're wonderful, all of them. Really great.
So this is the
famous stars.
Real thing.
Yeah, it had to happen when those two were less than 20 to 25 degrees above the horizon, and they're far south. So it's like, I've been trying to observe those two, and it's plagued with seeing conditions.
Okay, this is not from my backyard. This is, I went to the darkest spot in California, or maybe on the West Coast, Mesquite Springs and Death Valley. And all I got was 15 minutes of imaging. After that, something happened to my camera and it stopped working.
All the way out there, and that happens?
I went all the way out there just to do this imaging, and I only got 15 minutes of imaging.
That's a long drive for 15
So
minutes.
the first object that I tried was Andromeda Galaxy, and I just tried for 15 minutes, and I got this. I've imaged Andromeda Galaxy zillion times ever since I started astrophotography. But this 15 minutes is probably the best I've ever shot.
But look at the detail in the dust lanes. That's
That's
there's at
great.
least one cluster down in the lower right. I think that's a cluster.
Yeah, this one.
Yeah, that thing. Yeah, that thing.
And these guys here, these are all the emission nebulas in the galaxy.
Hey guys,
Also
cascades
of stars.
Hey guys, this is Spencer. I'm going to have to jump off, so I'm going to stop the YouTube recording, but I'll leave the session open for another 15 minutes or so if you guys want to hang around.
Spencer, thank you so much.
Thank you, Spencer.
All right.
Thanks, Spencer.
Spencer,
Okay.
we need to get you a coffee infusion.
I'm basically done.
Still can't believe that North America.